Explain how the pendulum in the Science Center is designed so it can be approximated as an ideal simple pendulum. An ideal simple pendulum? What is that? Well, let's go to the most trustworthy site, Wikipedia. You know it's good information because anyone anywhere can edit the site. Okay, that's sarcasm, sarcasm. But it's surprisingly good. Wikipedia is actually pretty good sometimes when it comes to physics. So, okay, simple gravity pendulum. What are the assumptions? Well, the rod or cord is massless. It doesn't stretch. It always remains taut. That's pretty straightforward. The bob, that's the ball at the end of the string, is a point mass. It has no volume. Motion only occurs in 2 dimensions. It doesn't go, kind of along an ellipse. It just goes back and forth on an arc. So that's definitely not true. I mean, in the Science Center, that thing is going around an entire circle. The motion does not lose energy due to friction or air resistance. The gravitational field is uniform, and the support, so what the pendulum is tied to, does not move. Let's focus on the most important of those. It is ideal if there is no friction, no air resistance, the string is massless, it does not stretch, inextensible, and the bob has no volume. The little ball at the end is a point mass. How do we get that to be pretty close to the actual design? Well, when you connect this thing, here's the pendulum. When you connect it, you probably want to use like a ball bearing or something really frictionless at the top. You get out your best friend, WD-40. You use a bunch of grease it up maybe. I don't know if they actually do that, but perhaps it would work. And you make this as frictionless as possible. There's something else we can do so it doesn't have air resistance. Air resistance, the force of air resistance, is proportional to the speed. We can approximate it that way. Sometimes we say speed, sometimes we say speed squared. Depends on the approximation you're looking for. But basically, the faster you're going, the more air resistance you feel. So how can we make this pendulum move back and forth slowly? What can we do to give it a slow speed? Well, for one, Wikipedia wants to come back. For one, okay, so the first thing we want to do, design to move slowly so that we reduce the air resistance. That's going to be pretty important, actually. And the way you make it move slowly is you give it a small amplitude. Don't pull it all the way back. Like if it were Miley Cyrus and it were a wrecking ball, she would swing it all the way back here, and it's going to swing all the way over and all the way back, and it's going to go faster. Don't pull it that far back, right? We don't need to go Miley on this pendulum. It's just the Science Center. It's for kids, after all. So, okay, that's the first thing, small amplitude. And the other thing is we want it to take a lot of time to go back and forth. Because, if it takes a long time, it's not going to go very fast. So what do we need? We need a large period. How can we make a large period? Well, let's look at our equation sheet. The period of a pendulum is 2 pi square root of the length divided by the acceleration due to gravity. Gravitational field strength is technically what that is. But what can we change? Well, you can't change 9.81. I mean, okay, maybe you can go to, let's see, we want a long period, so we need a small denominator. Maybe you could go to the top of Mount Everest, and g is a little weaker, but that's not what they're talking about. Look at the length. If you want a long period, you need a long length, a big numerator. So, large T, how do we make that happen? Use a long, make the pendulum long, a long length, L, or a long string, a chain, some sort of cable. How about a long cable, we'll say. Okay, so we've got this and this. The string is massless. Well, that's easy, right? We're going to use a cable, probably, And let's say the cable has a mass of 2 kilograms. If you put at the end 5 kilograms, make the bob, give it 5 kilograms, well, this does not seem so massless, does it? But if you choose something really, really heavy at the end, right, like let's say 5,000 kilograms, then now this 2 kilograms here is pretty negligible. So so what do we have to do for the massless string? You just make the bob, give the bob huge mass. So feed it lots of Twinkies, and then it's a high mass bob. Give bob huge mass. That's just a joke about Twinkies. Got Twinkies on the mind. How do we do the next one? String is inextensible. Well, you use something strong. Make the cable, use a cable for the string made from, wire. Don't make the cable out of rubber bands. It's not going to be inextensible. Rubber bands will stretch. So how do we give the bob no volume? Well, that's easy. Make the bob small. Easier said than done, right? Oops, we're running into, let's say, make the bob small. And so dense, if you use a really heavy, dense material, that would be good. But there's another way to make the bob look small. If you have the pendulum like this, well, the bob looks pretty large compared to the string. But if the pendulum is like this, that bob, which is the same exact size, by comparison, looks really tiny. So you can actually, this is another trick. You can just make the string long. Or the cable, I should say. Make the cable long. And that is a pretty exhaustive list. That's going to be way more than they're probably asking for. But it's, it's good to go through and be exhaustive. But just don't be extensible. Okay, let's solve the next part. If it is timed, so it takes 5 seconds to move from one side to the opposite side, then what is the length? Wow, it sure feels like I don't have enough information. I mean, all they gave me is 5 seconds. Presumably it's on Earth, right? So we know G is 9.8. It's going from one end. I want to understand, what is this 5 seconds? Is that like some random amount of time, delta t? Is it the period? Is it something else? Well, it's not the period, because the period would be the time to go over and then back. And this 5 seconds, that's the time just to get over to here. Oh, so then the period would be 10, right? If it takes 5 seconds to go over, the swinging is symmetric. It takes 5 seconds to get back. So the period is 10. All right, period, G, we're looking for L. Is there an equation with T, L, and G? Yes. The period of a pendulum is 2 pi radical L over G. Whoops. Period is 2 pi radical L over G. So we know T is 10. The length is our unknown. G is 9.8. We can divide both sides by the 2 pi, move that to the left, get rid of it first. 10 over 2 pi. You'll notice I always get rid of the 2 pi before I ever square and remove the radical. That's still under the radical. How do I get rid of the radical? We do the opposite, or the inverse function. We square both sides. Squaring is kind of the inverse of square root. And then the square root cancels the square. These they both go away. They cancel each other out. And I have, going up to here, I have 10 over 2 pi squared equals L over 9.8. I can multiply both sides now by 9.8. And I've got 10 over 2 pi equals L. I get out my trusty calculator, turn it on. It's funny, this thing, it's obviously an animation, but it'll still automatically turn off to conserve battery life. But it doesn't have a battery. I just find that funny. We do 9.8 times, open paren, 10 over 2 pi. Uh-oh, I'm doing it again, I'm making a mistake. And that's wrong. Oh, I make this, every time I do this, I make this mistake. Because remember, the calculator is dividing 10 over 2, it's doing 5 pi. I want pi in the denominator. So I need to put parentheses around the entire denominator. Close paren. So there, the denominator has parentheses around it, and then there's parentheses around the entire fraction, and I need to square that entire fraction. The other way you could do this is you could divide by multiply by 10 squared times 10 squared. Then I divide by 2 squared. You could just type over 4. Then I'm going to divide also by pi squared. So I'm taking the 10 squared. I want it divided by 4, and I want it also divided by pi squared. And this gives the exact same answer, 24.8. Is that the length? Oh, we don't have an answer on this one. 24.8. What's my unit? This is in meters per second squared. This is in seconds, and I square it, so it's now seconds squared. So the per second squared and the second squared, they cancel, and this is just meters.